Welcome back to Tade MedChem Insights. If you are a newcomer, don't forget to subscribe to the channel. I am Dr. Tadasa. Today we are going to deal with the medicinal chemistry of diuretics. This is a continuation of diuretics part 1, and here we are going to deal with loop diuretics, potassium-sparing diuretics, and osmotic diuretics, including their structure activity relationships. Let's go for it. Before directly going to our today's lesson, let's revise what we have discussed in diuretics part 1 video. So there we have discussed what does it means, what is their use, and we have seen some of the drugs. So just to remind shortly, diuretics are chemicals or drugs that increase the rate of urine formation. So for what purpose they are going to be used? They are going to be used in the treatment of edematous conditions and in the management of hypertension. So the edematous conditions results from a variety of causes such as congestive heart failure, nephrotic syndrome, and chronic liver diseases. These diuretics are powerful tools in the clinical conditions. They can often acting far beyond their conventional use. The conventional use of diuretics is to manage high blood pressure, that means hypertension, and edema. So they can also act beyond this as a sole or an adjunct therapy in the treatment of a wide range of clinical conditions such as hypercalcemia, diabetic insipidus, acute mountain sickness, primary hyperaldosteronism, and glaucoma. These all things are discussed well and in detail in the first part. Besides this, we have discussed also in part 1 some diuretics like carbonic anhydrase inhibitors and thiazide-like diuretics were discussed. So the carbonic anhydrase inhibitors, as the name indicates, they inhibit the enzyme carbonic anhydrase so that they can reduce the hydrogen secretion and the bicarbonate reabsorption. So generally they have a moderate kind of diuretic effect which can act on proximal convoluted tubule. The other is the thiazide and thiazide-like diuretics. Even though structurally they are different, pharmacologically they are the same. So they act in the distal convoluted tubules, and hence they inhibit the sodium chloride co-transporter so that they can reduce the sodium reabsorptions, and hence they have moderate diuretic effect. So today we are going to deal with 3 different drugs that act on the nephrons and anatomical sites, which have different mechanism of actions. So these are loop diuretics, potassium-sparing diuretics, and the osmotic diuretics. So the loop diuretics, as the name indicates, they act on the loop of Henle, particularly on the ascending loop of Henle, so that they can inhibit the sodium-potassium chloride co-transporter, so that they can drastically reduce the sodium reabsorptions. And these loop diuretics are the most potent diuretics. The other groups are the potassium-sparing diuretics. So these are the ones that can act in 2 different ways. Some of them act by blocking the epithelial sodium channel, which is found at the latest stage of the distal convoluted tubules, and the other is the one that acts on the collecting duct by inhibiting the aldosterone. So we have aldosterone antagonism, which are competitive inhibitor of the aldosterone by binding to the aldosterone receptors. The other is the one that can block the epithelial sodium channel so that they can inhibit the sodium reabsorption and potassium secretions. The third one for today is the osmotic diuretics. This is the one that can increase the osmolarity of filtrate so that they can hinder water reabsorptions. So these are the ones that we are going to discuss today. loop diuretics, potassium-sparing diuretics, and osmotic diuretics. Let's start with loop or high-selling diuretics. The diuretics in this class have extremely diverse chemical structures, and they are going to be used to control blood pressure so that they can be used in the treatment of hypertension. So when you are going to see the diverse chemical structures, so this loop diuretics have different classes. So this is based on their chemical structure. So we have organomercurial diuretics, we have sulfonamide derivatives, and we have non-sulfonamide loop diuretics. So when we see the organomercurial diuretics, we have different kinds of drugs. Currently they are obsolete, so we'll discuss each of them in detail. Now let's see with the organomercurials. So the organomercurials, as the name indicates, they contain organic molecules and also they contain mercury. So the name organomercurials was given. So these are agents that dominantly used as a diuretic therapy from 1920 to the early 1950s. So in the early 1950s, a drug known as acetazolamide was introduced, particularly in 1953, as an orally effective carbonic anhydrase inhibitor. So that before that, these organomercurials, which commonly require intramuscular injections, were the principal diuretics available. So how these organomercurials will elicit their diuresis? So they elicit their diuresis by inhibiting sodium ion reabsorptions at site 2. So site 2 is the thick ascending loop of Henle, and also they block the subsequent exchange of sodium ion for potassium ion. This is happen at site 4. So site 4 is the collecting duct. So that they are natriuretic effect and also chloruritic effect, and they have minimal caloritic effect. So natriuretic effect and that of chloruritic effect is the one that can enhance the excretion of sodium and chloride so that they can lead to reduction of fluid, and hence they can bring the diuresis effect. But these molecules have a lot of problems. So they have a lot of limitations. So to see the limitations, since they are going to be given through intramuscular, if they can be given orally, they cannot be relied on to elicit their diuresis. This is because of their poor and erratic absorption. Secondly, when they are going to be given parenterally, since they are going to be given through intramuscular, still they have 1 to 2 hour lag in the onset of diuresis. The third problem is that their ability to trigger diuretic response depends on the acid-base status of the patient or the individuals. That means they are totally ineffective when the urine of the patient is alkaline. And the fourth limitation is that they are toxic. They have cardiotoxicity and also they have nephrotoxicity. Because of this, the newly available drugs like the loop diuretics and others were discovered. Version of thiazide and thiazide-like diuretics, such as that of chlorothiazide, which is a prototype, and loop diuretics, such as furosemide, bumetanide, and ethacrynic acid, the use of organomercurials becomes obsolete. This is dominantly because of their limitations. So all of the limitations that were seen by the organomercurials were approved by the thiazide and thiazide diuretics and that of the loop diuretics. So these two drugs are importantly effective orally. So they have equally effective in both acidic and alkaline conditions, and also they can induce relatively rapid diuresis when they can be given parenterally, and also relatively they are non-toxic, so that they can improve the defects of organomercurials. Drugs that are going to be categorized under loop or high-selling diuretics are characterized more by their pharmacological similarity rather than their chemical similarity. That means they have a diverse chemical structures. Just to mention, furosemide is a prototype for those drugs that can be derived from antagonist acid, whereas bumetanide are the one that can be act as a prototype from those molecules that can be derived from that of methylic acid. Whereas the case of furosemide is the one that can be obtained from 4-amino-3 pyridine sulfonylurea. Whereas the ethacrynic acid is the one that can be obtained from phenoxyacetic acid derivatives. So that the loop diuretics or high-selling diuretics have diverse chemical structures, but they have the same pharmacological action. These drugs produce a peak diuresis much greater than the others, which are commonly used diuretics, so that the name high-selling diuretics is going to be given because of their peak diuresis. So they produce the peak diuresis as compared to other diuretics, and they can act distinctly on renal tubular functions, dominantly on the thick ascending loop of Henle, so that they inhibit the luminal sodium potassium chloride symporter. When we come to the mechanism of action of loop diuretics, they inhibit the reabsorption of sodium by inhibiting the sodium potassium chloride symport in the luminal membrane of the thick ascending lip of Henle. Besides that, they can increase the renal prostaglandin. As a result, they can bring dilation of blood vessels and reduce peripheral vascular resistance. This is very important for treating the high blood pressure. Besides that, they also have direct effect on vasculature, including increase in renal blood flow and increase in systemic venous capacitance. And generally, these high-selling diuretics are characterized by quick onset and short duration of actions. So that means their diuretic effect appears in approximately 30 minutes and lasts for approximately 6 hours. The loop diuretics has two major classes that are clinically utilized. So these are sulfonamide derivative and the non-sulfonamide derivatives. And again, the sulfonamide derivatives have two classifications. So these are 5-sulfonyl benzoic acid derivative, and the other is 4-amino-3 pyridine sulfonylurea derivatives. So these are three classes. So for the case of the sulfonyl benzoic acid derivative, we have two classes, the bumetanide and that of the furosemide. Both of them have the sulfonamide groups. In the case of furosemide, also they contain the sulfonamide groups, but it is derivative. But the case of non-sulfonamide loop diuretics, so the ethacrynic acid is the only one which does not contain any kind of sulfonamide groups. And again, the 5-sulfonyl derivative can also have two series based on the nature of functional group that are going to be substituted at position 2 and position 3 of the drugs. If the substitution will be happen at position 2, here is a position 2, so they are going to be taken as 5-sulfonyl 2-amino-benzoic acid derivative that come dominantly from antagonist acid derivative. So furosemide is a prototype for this group. If the functional group substitution, it will be takes place at position 3 in the case of bumetanide, which is a prototype. They are named as 5-sulfonyl 3-amino-benzoic acid, or they are going to be derivatized from methylic acid derivatives. So we'll discuss each of them in detail. Now let's see the structure-activity relationships of sulfonamide derivatives. When we are going to deal with the development of the loop diuretics, it is an extension of the research that involves the thiazide and thiazide-like diuretics. So there are important structural requirements that are going to be needed and which are considered to be common for the sulfonamide derivatives to act as a loop diuretics. So these common structures will include the 5-sulfonyl 2-aminobenzoic acid derivative and the 5-sulfonyl 3-aminobenzoic acid derivatives. For the first case, that means for the case of 5-sulfonyl 2-aminobenzoic acid derivative, the furosemide is the prototype. For the second case, 5-sulfonyl 3-aminobenzoic acid derivative, the bumetanide is a prototype. So generally, these derivatives were considered, they are going to be taken from the antagonist acid or the ortho-aminobenzoic acid. As you have seen from the structure here, this is the antagonist acid, or we can see that it is ortho, the amine group is found at ortho side, ortho-aminobenzoic acid. So they are going to be derivatized from this one by simply adding at the previous positions. The numbering starts from the carboxylic acid 1, 2, 3, 4, 5. So the sulfonyl group is going to be found at position 5. So the derivative 5-sulfonyl antagonist acid is going to be taken as the starting point for these two prototype drugs, the furosemide and that of the bumetanide molecules. So generally, they are going to be differentiated because of the functional group that are going to be added at position 2 in the case of furosemide analog, and in the case of bumetanide analog, the amine group is going to be found at position 3. So when it comes to the structure activity relationship in detail, so the presence of the acidic molecules or acidic moiety at position 1 is essential for the optimal diuretic activity of the molecules. So the carboxylic acid is here, as you have seen in both of the molecules. So this is the one that can provide the maximal or the optimal diuretic activity. So acidic group should be there here. Not only carboxylic acid, but also it's possible to change the carboxylic acid by tetrazole. So tetrazole also acidic, so they can also bring the acidic functional group. Just to see on the structure of the molecules, for the case of the first one is the furosemide, for the second part is the bumetanide. Both of them contains at the first position, they contains the carboxylic acid, which gave them the maximum diuretic activity. This is other SAR of sulfonamide derivatives. So we'll come to the sulfonyl groups, which is found at position 5. As you have seen in all of the molecules, they contain free sulfonyl groups that are substituted at position 5. So this is a prerequisite for optimal high saline diuretics. So the sulfonyl group should be free. It is unsubstituted for optimizing the activity of loop diuretics. The other is the one that is found at position 4 in both cases, that is X. So X contains dominantly the chloride or trifluoromethyl substituents, so which is similar to that of the thiazide and thiazide-like diuretics. For the case of thiazide-like diuretics and thiazide, so here we have the chlorothiazide, which is the thiazide diuretics. So it contains also chloride, which is ortho to that of the sulfonyl groups, which is similar to that of the loop diuretics. Then if we are going to replace this the chloride and the trifluoromethyl groups by other substances like phenoxy groups, or in the case of the bumetanide, so we have the phenoxy group is going to be there, or by alkoxy group, by anilide, benzyl or benzoyl moieties. So the phenoxy group is the one which can act as an electron withdrawing groups. So these phenoxy groups totally replace the customary chloro or trifluoromethyl substances that can be seen in other substances and other diuretic moieties like that of thiazides and thiazide-like diuretics, and also the furosemide analog. So this phenoxy group is an electron withdrawing groups that is similar to that of the chloro and trifluoromethyl groups. So this minor variation between that of bumetanide from that of furosemide produce a compound with a mode of action similar to that of furosemide, but with marked increase in terms of the diuretic potency. But don't forget that their short duration of action is similar, but the compound that contains phenoxy is approximately 50 times active in terms of potency. In such a case, the bumetanide is more potent than that of the furosemide because of the presence of the phenoxy groups. So, but if we are going to replace these 5 substances, the phenoxy, alkoxy, aniline, benzyl, and benzoyl moiety, to that of the thiazide and thiazide-like diuretics, as you have seen here, this is the chlorothiazide. If replace the chloro group by these molecules, the activity is going to be decreased. So replacement of the phenoxy group is also possible at position 4 for the case of bumetanide with other moieties. For this is at position 4, we can replace by phenyl amino group. It's possible by the phenyl anilo groups, also possible by the benzeno-thiazole group is possible. So these molecules also be replaced. The phenoxy group can also be replaced. That can bring a potent molecules like that of the phenyl amino and the benzene thiolate groups also possible. Sometimes you can also replace by anilo groups, which can give a better activity in terms of their potency. To continue the SAR of sulfonamide, the amino groups that are customarily found at position 2 in the case of the furosemide series has been moved from position 2 to position 3 in the case of the bumetanide and its analog series. You see, so this is the position 3, this is the position 2. So this is a furosemide series or analog. This is the bumetanide series where the amino group is found at position 3. So what is going to be there? You see, as you have seen, all of the molecules contains at position 2 for the case of furosemide, and for the case of bumetanide, they contains at position 3. So the substitution on amino groups is going to be there. So R group is substituent for the case of furosemide at position 2 on the amino ring systems, and also we have R for the case of bumetanide series that are going to be substituted at position 3. So when we consider the furosemide case, the substitution on the amine group is limited. So they contains the furfuryl groups. So as we have seen here, the order is also like that. The one that contains the furfuryl group is more potent, as we have seen the case of the furosemide ring systems. Then they also be replaced by benzyl groups or thionyl methyl group. This is the benzyl groups. That is the thionyl methyl group. This is the maximum moiety that should be replaced for the case of amine substances in the case of 5-sulfonyl 2-aminobenzoic acid derivatives. But in the case of the 5-sulfonyl 3-aminobenzoic acid derivatives, that is the case of the bumetanide series. So the 3 amino group, this is the 3 amino groups, can be substituted by a lot of molecules without much changing in the activity. For example, it can be replaced by alkyl substances, and as the case of the bumetanide itself. So this is the butyl side chains, and also in the case of pyrazinoylguanidine, they contains cyclic ring system. So cyclic ring system is also possible to replace at position 3, or we can replace by any kind of alkyl groups as the case of bumetanide. So that does not bring any kind of change in their activity. So there is a possibility that we can use widely substitute group may replace on the R group of the position 3 of the amine groups. But in the case of the furosemide, we only have 3 substituents, that is the furfuryl, the benzyl and the thionyl meta group. These are the substances. These are the only substances with the furfuryl group is with the maximum activity, as we have seen in the case of the furosemide. Now let's come to the non-sulfonamide derivatives. As we have seen earlier, most of the loop diuretics are considered to be sulfonamide derivatives. The one which we have taken as the bumetanide and the furosemide as the prototype. So the ethacrynic acid was developed at about the same times as furosemide is going to be developed, but were designed to act as mechanistically similar to that of the organomercurials diuretics, which was obsolete when the thiazide and thiazide-like diuretics and that of the loop diuretics were discovered. So this ethacrynic acid acts through inhibition of the sulfhydryl containing enzymes that can involve in solute reabsorptions. So this sulfonamide group is the one that contains the substances like sulfur and hydrogen molecules. Those which contains the sulfur and hydrogen molecules can be considered to be the sulfhydryl containing enzymes. So based on that, the ethacrynic acid was designed to mimic the mercurial diuretics activity. So when we see the detailed discovery of the ethacrynic acid, so furosemide was widely used loop diuretics, as we have seen that. It was discovered in 1959. So based on that, ethacrynic acid was discovered and developed in the early 1950s by researchers at Merck, Sharp, and Dahomey laboratories in the Pennsylvania, United States. It was introduced as a potent loop diuretics in the early 1960s, with clinical studies appearing in the mid-1960s before receiving the FDA approval for widespread use in 1967. So these are structures, as we have seen that this molecule does not contain any kind of sulfonamide group, so that's why we can say that it is a non-sulfonamide derivative. This is only molecules. This is the only molecules which can be considered to be the one that have similar action as that of the other diuretics by inhibiting the sodium potassium chloride symporter in the ascending limb of loop of Henle, so that it can promote a marked diuretic activity as that of the furosemide and the other bumetanide analogs. So this ethacrynic acid is the only loop diuretics that is not a sulfonamide derivative. Remember, it is only loop diuretics that is not a sulfonamide derivative, and it is may be useful in patients who are allergic to sulfonamides. Now let's come to the structure activity relationships of ethacrynic acid. So that is the only non-sulfonamide derivative. So this is a molecule that was derivatized from phenoxyacetic acid molecules. So this is the phenoxy groups. So this is acetic acid. So ethacrynic acid is a phenoxyacetic acid derivative. So increased activity is going to be observed in the case of the ethacrynic acid when an electron withdrawing groups such as chloride is placed ortho to that of the unsaturated the keto ring systems that are very important for binding to the active site of the sulfhydryl molecules of the receptors. So that is the ortho part should be there. So it is also one of the important requirement to make the drug active, so they can bind to the active site of the enzyme that contains the sulfhydryl moiety. Another thing that ortho and meta substitutions regarding to that of the unsaturated keto moiety. So this is ortho and this is meta positions, which is the di substitution with chlorine molecules also produce the most active compounds, as we have seen in the case of ethacrynic acid. So they contains ortho and meta di substitution of chloride. So this will produce the most active compounds. So optimal diuretic activity was observed when the acryloyl moiety, this is the acryl moiety as you have seen here, when we have the acryl moiety is going to be there. So this is the one that can react with the sulfhydryl containing receptors that are going to be found in the renal tissue, because the loop of Henle is the one that contains this moiety, was positioned at the para position of the oxyacetic acid. Just this is a benzene, so when considered that the acetic acid and the oxy part here, so the acrylyl moiety should be found to the para position of the oxyacetic acid, and also they should contain the chloro groups, or sometimes methyl groups can be also there at position 2 or 3. So this kind of molecules, when considered to that of the position of the firing systems, will bring the optimal diuretic activity. So in short, to have an optimal diuretic activity, the acrylyl moiety should be para to that of the oxyacetic acid derivatives that are attached to the benzene systems, and it must also contain either chloride or methyl groups either at position 2 or position 3, but dominantly position 2 is more preferably to be chloride, because this is the one that can bind to the active site of the enzyme, so that it can bind with the sulfhydryl groups. So if we are going to replace the group, so methyl group can replace this position. The position 2 of chloride can be possible to replace with methyl groups to have an optimal diuretic activity. So if we are going to reduce or epoxide the acryloyl moiety of this double bond, the carbon-carbon double bond, if we can reduce, that means if we can make it saturated, or if we can make the molecule to contain an epoxide characteristics, that means the one that contains like this, so the activity of the molecule is going to be totally lost, or it may have very little activity. That means if we are going to reduce the double bond here to be saturated, so they have little diuretic activity, and if we can make the molecule to have an epoxide characteristics, so they totally lost their diuretic activity, so that the double bond that are going to be found in the acrylyl moiety is essential for optimal diuretic activity of the ethacrynic acid. Now let's come to the other diuretics, that is potassium-sparing diuretics. So these diuretics act on two sides dominantly, the late distal convoluted tubule and the collecting duct. Hence, they have limited ability to affect the sodium absorption. Because of that, they have a mild diuresis. The most important adverse effect associated with these agents, that means the potassium-sparing diuretics, are their potential to contribute to hyperkalemia. So they are crucial for preventing potassium loss. Dominantly, because of this action, potassium-sparing diuretics can be used as an adjunct, specifically with that of the loop diuretics and the thiazide-like diuretics. Because in the case of loop diuretics and thiazide-like diuretics and thiazide itself, so one of the side effects that can be associated is they can deplete potassium. So potassium depletion is one of the side effects, specifically for the case of loop diuretics. So the depletion of potassium is more severe. So to avoid the depletion of potassium, potassium-sparing diuretics can be given with that of the loop diuretics and the thiazide and thiazide-like diuretics. So it can alleviate the severe depletion of potassium, specifically in the case of loop diuretics. So what are the therapeutic use of potassium-sparing diuretics? So they can be used for edema associated with hyperaldosteronism, specifically for the case of hepatic cirrhosis and nephrotic syndrome. They can also be used in the case of heart failure. So it can be used to reduce mortality by preventing myocardial fibrosis. and also it can be used for resistance, hypertension, and primary aldosteronism. So there are two main subclasses when we are going to talk about potassium-sparing diuretics based on their action. These are known as aldosterone antagonism, or sometimes they can also named as mineralocorticoid receptor antagonists. So an example is the spironolactones is one of the important examples, and also they can act on the epithelial sodium channel blockers. As an example, Triamterene is one of the examples. So the case of the epithelial sodium channel blockers are mostly act on the late distal convoluted tubules, whereas the aldosterone antagonism or the mineralocorticoid receptor antagonisms act on the collecting duct. The mechanism of action of potassium-sparing diuretics. So they promote diuresis and reduce blood pressure without potassium loss by inhibiting sodium reabsorptions in the collecting tubule and the late distal convoluted tubule. So that they work either by blocking the epithelial sodium channel directly or by inhibiting aldosterone receptors, which reduce sodium potassium exchange. So when they can act here, this is the receptors. When they act here, so they can reduce the sodium potassium exchange. So for the case of the epithelial sodium channel inhibition, so they act here, so they can inhibit the possible reabsorption of sodium ion. So they can act as competitive antagonists, specifically when they can act as an aldosterone antagonism at the intracellular mineralocorticoid receptors. That is here. This is the way when they can act here. For example, if the spironolactones act by binding to the mineralocorticoid receptors, so they can compete with the aldosterone, so that they can inhibit the binding of aldosterone and hence can prevent the synthesis of proteins, including the epithelial sodium channels that promote sodium reabsorption and potassium excretion. So by doing this, they can block the aldosterone binding and they can prevent the translocation of the receptor complex to the nucleus. So generally, as a result, so the potassium-sparing diuretics by binding to the epithelial sodium channels blocking effect and also by inhibiting the aldosterone receptors, so they can decrease the gene transcription for epithelial sodium channel and basolateral sodium potassium ATPase pump. This is a sodium potassium ATPase pump, so that they can decrease the sodium reabsorptions, specifically in the case of the epithelial sodium channel blocking conditions, and also they can inhibit simultaneously, they can prevent the coupled secretion of potassium and hydrogen ions. So that is the important role of the potassium-sparing diuretics. And generally, to see what are the key pharmacological effects of potassium-sparing diuretics, one of the thing is they can act as diuresis, so they can increase sodium excretion, so that can lead to increased water excretions, specifically when they can act on the blocking of the epithelial sodium channel. And also they can act as potassium retention, so they can block the exchange of mechanism of potassium and sodium, so that the potassium remains in the blood rather than being secreted into the urine. So they can retain the potassium ions. That's also another important role. The other is it has a kind of synergetic activity, since it can be combined with other diuretics such as with loop and thiazide-like diuretics. And thiazide itself, they can prevent the hypokalemia effect. So because these loop diuretics and thiazide-like diuretics have a kind of side effect that excessively lose potassium, but when they can be combined with potassium-sparing diuretics, so they can bring synergetic activity, since the potassium-sparing diuretics will retain the potassium, so that the depletion of the potassium is going to be protected. And generally, when we consider to the clinical application of potassium-sparing diuretics, they can be used generally to treat hypertension, heart failure, and edema, particularly when managing hypokalemia. So actually they are contraindicated in patients with existing hyperkalemia or severe kidney disease. We have to avoid giving potassium-sparing diuretics for those individuals which have hyperkalemia and which have severe kidney diseases. Let's come to the aldosterone antagonists. So aldosterone is the one that can be secreted from the adrenal cortex. So it is one of the potent mineralocorticoids that promote the salt and water retention and also potassium and hydrogen ion excretion. So aldosterone exerts its biological actions by binding to the mineralocorticoid receptor. So we have also other mineralocorticoid molecules which have an effect on electrolyte balance of our body, but the aldosterone is one of the most potent. When we compare with other molecules in terms of increasing their absorption of sodium and chloride ions and increasing potassium and hydrogen ion excretion, so the aldosterone is the most potent. For example, if you compare to that of hydrocortisone, aldosterone has 3,000 more active than that of the hydrocortisone. So aldosterone can exist in two forms. It can exist as form of aldol, or it can exist as form of hemiacetal form. So this is a hemiacetal form. Here we have the aldehyde part is there. So when the aldehyde will interact with that of the OH groups, they can produce the hemiacetal form. Both of them are active. So a substance that can antagonize the action of aldosterones are considered to be a good diuretics drug. For example, spironolactones and the prenols are very good examples that can antagonize the action of the aldosterones. So these drugs can also be named as mineralocorticoid receptor antagonists. When we see the structures, they have two important differences. One, in the case of the prenol, they contain the epoxy groups, and the other thing is that in the case of the spirolactose, they contain some sulfur groups, but here we don't have sulfur groups in the case of the prenols. So that's the basic difference between the two most effective aldosterone antagonist drugs. Let's discuss the structure-activity relationship of aldosterone antagonists. So the steroidal structure of the antagonist is very important. As you have seen from the structure, they should contain the steroidal scaffold. So this is one of the requirements to have a highly specific steroidal nucleus that can easily bind to the mineralocorticoid receptor. So if they contain these ring systems, so this is ring A, this is ring B, this is ring C, and this is ring D. So the one that contains these four ring systems are named as steroid. So having a steroid scaffold is essential for the molecule to antagonize the action of the aldosterones for binding competitively to that of the mineralocorticoid receptors. So that both drugs have such kind of ring system. So the mineralocorticoid receptor antagonist activity of the spirolactones depends on the presence of two important structures. One is at carbon 70, here is carbon 70, so this carbon 70, they contains gamma lactoring systems. So this is a gamma lactoring system. So this is essential for antagonist activity of the drug. But if you are going to open the ring, of the gamma lactoring systems, so the activity is lost. So it's a must that the lactoring system should be closed. The other important ring systems that is essential for binding to the receptors and help to antagonize the aldosterone is the carbon 7 alpha acetyl thio ring system. This is acetyl part, this is the sulfur, so that's why thio is going to be there. So this carbon 7, so at carbon 7 we have the alpha acetyl thio group. So why alpha? So the ring system is the substance or the moiety is away from the observer if we are going to see the 3D ring system of the drug. So this is the one that can increase the oral bioavailability of the drug, and also it can protect the carbon 7 position from rapid metabolic inactivation. The other importance of this moiety is interaction of carbon 7 and substitute agonists, such as the case of aldosterone. If they don't contain these alpha acetyl thio groups, as in the case of aldosterols, with a methionine residue in the mineralocorticoid receptor ligand binding domain, is important for receptor activations, and also they can bring subsequent transcription. But if this part is going to be substituted by that of the alpha acetyl thio groups, so that this molecule sterically hinder this carbon 7 position or substance of the aldosterone, so they can antagonize, so thereby they can bring the mineralocorticoid receptors is going to be inactive conformation. So that's very important. So these are the two important structures that can bring the antagonist activity of the spironolactones molecule. Let's come to the other part of the SAR of aldosterols. So we have seen the case of the spironolactones. Now let's come to the pyranol cases. So in the case of the pyranol, so this also contains the steroidal scaffold. It's a must to bind to the mineralocorticoid receptor. So the pyranol also contains the steroid nucleus. So this is ring A. So this is ring B. This is ring C. And this is ring D. So they contains the steroidal skeleton, so they can help the molecule to bind to the mineralocorticoid receptor, so they can antagonize the aldosterols. So when we are going to see the drug, it is a newer spironolactones analog with reduced adverse effects. So the case of the phenols, in addition to the lactone ring system and carbon 7, actually in the case of here the carbon 7 is the case of here is does not contain sulfur. This is acetyl groups. They also have additional molecules at the carbon 9 and 11. So that is a little bit newer case for the case of the pyranol. So they have three important structure or moiety that are going to be found in the case of the pyranol. So the first part is the carbon 17 gamma lactone ring systems, which is similar to that of the spironolactone. So they are essential for antagonist activity, and if we open the ring, the activity drops significantly. The other ring is at carbon 7, we have the alpha acetyl groups, but in the case of spironolactones, they contains alpha acetyl thiol. There is sulfur groups, but in the case of the pyranol, we don't have sulfur. Here only we have the alpha acetyl groups. So this is also very important as the moiety. So this is the case of the spironolactones. They contain sulfur, so the alpha acetyl thiol, but here it is only alpha acetyl groups. So this is important for the mineralocorticoid receptor antagonism. And the third, which is specific to that of the pyranol, is it contains carbon 99 alpha and carbon 11 alpha epoxy groups. So this is the part. So this is the part. So this is the one that make differ from that of the spironolactones. So this structure addition of the pyranol's cause a significant steric change, so dramatically reduce its affinity for androgen and progesterone receptors. So when we are going to compare the activity, it has 20 to 40 times lower affinity for binding to the mineralocorticoid receptors as compared to the spironolactones. As a result, it has much more selectivity for the mineralocorticoid receptors than that of the spironolactones. So this can result with a significant fewer endocrine side effects. Here, don't forget that the reduced binding capacity of pyrenols is going to be happen because of the presence of the epoxide group that are found in position carbon 9 alpha and carbon 11 parts. Let's come to the second group of potassium-sparing diuretics, that is known as epithelial sodium channel blockers. So the amiloride and the triamterene are very good examples of these blockers. So the triamterene and the amilorides are often prescribed with potassium wasting diuretics in an attempt to mitigate the loss of potassium. When administered as a single entity or as one component of a combination product, this agent result in moderate diuresis. So when we are going to see the mechanism of action of these drugs, dominantly they are going to be used directly and reversibly block the luminal epithelial sodium channel in the late distal convoluted tubule and collecting ducts. So at that they plug the channel pore. So because sodium ion reabsorption creates a luminal negative electrical potential that drives potassium and hydrogen ion out of the cell. So blocking the sodium ion at the epithelial sodium channel entry dissipates this electrical gradient. As a result, these drugs, the amiloride and the triamterene, are the ones that directly inhibit the reabsorption of sodium ions, and indirectly they inhibit the potassium and hydrogen ion secretions. So generally these drugs are going to be combined with thiazide or loop diuretics that are going to be used to treat edema and hypertension. So when we come to the therapeutic use, they are rarely used alone due to its low diuretic efficacy. So as I've already said, they are going to be combined with either with the thiazide or with the loop diuretics, because the thiazide and loop diuretics are the ones that can cause potassium depletion, so that this potassium depletion can be counteracted by the epithelial sodium channel blockers. So because of that, primarily it can be co-administered with that of the loop and thiazide diuretics, just to counteract the severe potassium loss because of the loop or thiazide diuretics that bring hypokalemia. So that dominantly they can be used as a co-administered drug, and also they can be used for treatment of Liddle syndrome. Specifically, the amiloride one are the one that can be used for such syndrome. What does it mean by Liddle syndrome? So this Liddle syndrome is a rare autosomal dominant genetic disorder causing early onset severe hypertension and also low potassium, that is hypokalemia, and metabolic acidosis due to mutation in the epithelial sodium channel. So that it can cause excessive sodium reabsorptions in the kidney that can often appear in children dominantly and also young adults. So as I've already said, the treatment involves the blocking of the epithelial sodium channel just using the aminorides. Now let's come to the structure-activity relationship of epithelial sodium channel blockers, starting from the amiloride. So this is the amiloride structure. So both of the amiloride and that of the triamterene are organic bases by their natures. So because they contain a lot of amine groups, as we have seen from their structures, so they exist primarily in their protonated or cationic forms at physiologic pH. So this helps them or allow them to block the sodium ion pore in the epithelial sodium channels at the late distal convoluted tubule and collecting duct. So individually, the amiloride and the triamterene exerts a mild diuretic effect and are usually used in combination with thiazide or that of the loop diuretics. So inhibition occurs because the amiloride and that of the triamterene bind to negatively charged regions of the sodium channel in the epithelial sodium channel, so that they can block the reabsorption of sodium ion and they can inhibit the secretion of potassium and hydrogen ions. Generally, when you are going to see the oral the amilorides is approximately 50% absorbed with a duration of action of 10 to 12 hours, which is slightly longer than that of the triamterene. So actually the amilorides also exist as form of aerosol form. It has shown some benefit in improving the mucociliary clearance in patients with cystic fibrosis. So let's start from that of the amiloride. We are going to deal with the structure part, the structure-activity relationship of the molecules. So the amilorides are a pyrazinoylguanidine moiety. So this is the pyrazine. So they have the amine parts, and this is all the guanine part. So they contain the guanine part. So they can made from these molecules. So the pyrazine, so I've seen the structure, this part. So they have the amino parts. So the aminopyrazine there. So they also contains the guanine moiety. It is so that we can say that the amiloride is an aminopyrazine structure related molecules. So structural they are similar to that of the triamterene because both of them are derived from the aminopyrazine. We see if we are going to see structure of the triamterene, also they contains the aminopyrazine ring systems. So but in the case of the amiloride, so it's not fused ring systems, but this is a fused ring systems. So the one that can also include the guanidine moiety. So both of them does not have effect on the action of aldosterone. So features of guanine group is very important for bringing the basic characteristics with pK of 8.7. It is protonated at physiological pH, as you already said that this is an important part that allows the molecule to block the sodium ion pore in the epithelial sodium channels, just block. And this positive charge is critical for plugging to the epithelial sodium channel pore. So optimal activity is going to be required just where we are going to have the amino groups. So the amino groups should be found at position 3 and 5 of the pyrazine ring system. That's one important requirement to bring the optimal activity. Another thing that electronegative chlorine should also be found at the position 6 of the pyrazine ring. So this is the one that can give the optimal activity of the amiloride. So the presence of amine groups at position 3 and 5 and the presence of the chloride at position 6 of the pyrazine ring system is important, or it is a requirement to bring the optimal activity of the drug to bind to the epithelial sodium channel. Let's continue the structure-activity relationship of epithelial sodium channel blockers by considering the triamterene. So triamterene is pyridine derivatives. Actually, this is a pyridine molecules. Pyridine have a marked potential for influencing biological processes. So before obtaining the triamterene, so these molecules, the 2,4-diamino 6,7-dimethyl pyridine was made, and these molecules have a fairly potent diuretic activity, which was derivatized from that of pyridine. So further structural modifications of the pyridine nucleus led to the development of the triamterene. So that is the triamterene. So they have some modifications on the structures. So amino groups are added, and also the phenaric system is also added. So when we compare the amiloride with that of the triamterene, so they are structurally they are distinct, but they have similar pharmacophore footnotes. Both of them, the triamterene and that of the amilorides, contains the amino pyrazine molecules. This is the amino pyrazine molecules, which is common pharmacophore footprint for both of them. So when you come to the triamterene, so it requires amino groups at position 2, 4, and 7. That of the pyridine ring system. So numbering starts from here. So this nitrogen is 1. So this is 2. So this is 3. This is 4. Then this is 5. Then this is 6, and this is 7. Then this is 8 actually. So the amino groups at position 2, position 4, and position 7 are very important. It is a requirement for the molecule to bring the diuretic activity. So, and again, the phenaric system is also there. The phenaric systems at position 6 is also crucial for its binding affinity and the overall diuretic activity. So this is the benzene ring. That is also one of the important molecules for binding to that of the epithelial sodium channel to block the action of the molecules totally. Then structural modifications of triamterene structures are not usually beneficial in terms of the diuretic activity. A lot of SAR was started, but none of them have superior over that of the triamterene. So what was made that activity is retained if the amino groups, these are the amino groups at position 2, 4, and 7 are the amino groups. If they are going to be replaced by lower alkyl amine groups, the activity remains the same. It retains, does not boost the activity. On the phenaric systems, so paramethyl groups are going to be tried, but they can decrease the activity approximately by half. And also the para-hydroxyl group also tried, but these para-hydroxyl groups also make the molecule to be inactive as diuretics. So none of the structural modification on the triamterene structures are beneficial over that of the drug itself. We reach to the final part of diuretics, that is osmotic diuretics. Osmotic diuretics are pharmacologically inert. They are highly water-soluble compounds that increase urine output by enhancing the osmotic pressure of the glomerulus filtrate, so that they can prevent the water reabsorption in the nephrons. So they are agents that mobilize fluids by increasing the osmotic pressure in the tubules, and they operate primarily in the proximal convoluted tubule and in the descending limb of the loop of Henle. And as I've already said, that they are pharmacologically inert molecules that alter the osmolarity of the glomerular filtrate, so that they can prevent the water reabsorptions in the nephrons. So there are a number of simple hydrophilic chemical substances are there that are filtered through the glomerulus, such as that of the mannitol and the isosorbides. Actually, the mannitol is the prototype from the group. So these molecules are the one that can have ability to carry water within them in the tubular fluid. When we are going to see the mechanism of action of the osmotic diuretics, unlike other diuretics, they do not interact with a specific receptor or enzyme. They are freely filtered at the glomerulus but undergo virtually no tubular reabsorptions, and hence they increase the osmolarity of the tubular fluid so that they can exert an osmotic pressure that holds water in the lumen, especially in the proximal convoluted tubule and the descending limb of the loop of Henle. So they also exert water from intracellular compartments into the extracellular fluid so that they can expand the blood volume and decreasing blood viscosity before undergoing renal excretion. When we come to the therapeutic uses, they prompt reduce of elevated intracranial pressure, so specifically in the cerebral edema cases. They also help in reduction of intraocular pressure before ophthalmic surgery, dominantly for the case of acute angle closure glaucoma, and also they can be used as a prophylaxis of acute renal failure. Just this is to maintain urine flow in settings of severe trauma or ischemia. Let's come to the final part of our discussion, that is the structure-activity relationship of osmotic diuretics. To start with, let's start from the design constraints. To act as an osmotic diuretics, a molecule must possess the following four distinct chemical or pharmacokinetic traits. The first one is should have low molecular weight. This helps the drug to be freely filtered by the glomerulus. The other thing is that it should have highly water soluble. This helps also to remain in the aqueous filtrate. The other thing that it should have poorly reabsorbed by the renal tubule. And the final part is resistance to significant metabolic degradation. So we do have key structural characterization where we are going to design osmotic diuretics. The first is the molecular structures. Just to take the protopically osmotic diuretics like that of the mannitols, they are polyols. They contain sugar alcohols, while others may contain glycerols or isosorbides. All of them contain an OH molecules. The other structural characteristics is the hydrophilicity of the molecules. The presence of multiple hydroxyl groups is crucial, which allow the molecule to have high solubility in the tubular fluid so that it remains in the aqueous filtrate. And they have and this make also to have a minimal membrane permeability, which restricts their reabsorption. That's why they have a poor reabsorption by the renal tubulars. The other key structural characteristics is that they are inert in nature. These agents must not act on specific receptors or enzymes or ion channels. They function solely through their osmotic pressure to inhibit water reabsorptions in the descending limb of the loop of Henle and the proximal convoluted tubule. Let's see the prototype, that's mannitol. Mannitol is the one that can be obtained from mannose by reducing the aldehyde form to alcohol. So it is a 6-carbon sugar alcohol. As we have already said, that one of the key structural characteristics, it should contain a number of hydroxyl groups, so it is polyol. So it is a reduced form of the mannose. So this is the mannose, the D and the L form of the mannose. So the mannose contains the aldehyde. So this aldehyde is going to be reduced to the alcohol form. That is what we can obtain the respective mannitol. The D form of the mannose will give the D form of the mannitol. The L form will give the L form of the mannitol. So the aldehyde is going to be reduced to alcohol, and it contains 6 carbon atoms. So as we have seen that 1, 2, 3, 4, 5, 6, and also they contain 6 hydroxyl groups are there. So they contain 6 OH groups, 1, 2, 3, 4, 5, 6. So these 6 hydroxyl groups make it extremely hydrophilic. Because of its highly polar nature, it cannot easily cross the lipid bilayer like that of the gastrointestinal tract, and thus must be administered intravenously. The other example is the isosorbide. This is the structure of isosorbide. So this is a bicyclic molecules, as we have seen. It is made from two fused Furan ring systems. This is one Furan ring system, this is another Furan ring systems, and also they contains two hydroxyl groups. So this is the one that make also the hydrophilic characteristics. Actually, when you compare the isosorbide with that of the mannitols, the isosorbide is less polar than that of the mannitol. So this allows for oral absorptions and is primarily used orally for reductions of intraocular pressure. With this, we conclude the diuretics. Specifically today we have seen the loop, potassium-sparing diuretics, and osmotic diuretics. Thank you for watching. If you are a newcomer, don't forget to subscribe, and we'll see in the next time with new educational video. Thank you very much.